Bismillah ar-Rahman ar-Rahim. In the previous lecture, we discussed the example or we discussed the design procedure for synchronous sequential circuits. And we looked at basically two applications. One application is called sequence detection applications, and the other application is code detection applications, okay? And for sequence detectors, we only covered the cases where we allow overlaps, but you should be able to generalize that to not allowing overlaps, okay? For code detectors, it's always with no overlaps, okay? So let's see, examine the difference between the two sequence and code detection applications, okay? Let's examine and understand the difference, the key difference between the two applications. First of all, a sequence is a variable length string of bits, okay? It's a variable length string of bits. And the target in this case, the target string we look for may be anywhere in the string, okay? So it can be at the beginning, at the end, in the middle, wherever that can be, okay? We don't know the length of the sequence ahead of time, and we are basically receiving a bit by bit through a serial input, like X or Y or whatever the input is, okay? And we are examining the sequence or building the sequence as we go, and we are looking for a certain sequence. Let's take an example. So we would like to target the sequence, or our target sequence is 1101, okay? And we have this serial data here. This is basically X at every clock cycle, okay? X at every clock cycle. Remember that we have like a clocked sequential circuit here, okay? And we have X coming in as one bit every clock cycle. This is the clock here, clock, CLK. And this is my Y, which says either 1 or 0, depending whether the sequence is detected or not, okay, at that clock cycle. So at the beginning, we have like 1, 1, 1, and then something interesting happens, okay? So I made a mistake here. The sequence must be actually, let me just erase this. That, yeah, I can just erase that. Okay. All right, and the sequence actually is not 1011, it's 1100. So this is the sequence 1101. I'm sorry, 1101. Okay, and let me highlight this sequence. So as soon as we see the sequence, my output will be asserted 1. Okay, so I'm just highlighting the sequence now. Okay, and then some random data occurs without the sequence showing. Okay, and then we have some so 00011 and then 1101. So this is our sequence again. Okay, so this is an occurrence, another occurrence. So my Y will be asserted 1 here. Okay, then we have also, again, it's not this actually, it's this one. Okay, this one here. All right, 1101. Okay, 1101. So, and this one I need to pull it a little bit. Okay, so I underline the correct sequence. Okay, so basically now the sequence here appears one after the other. Exactly. There is no overlap between this sequence here and this sequence here. Okay, so they are completely isolated, as well as this sequence. There is no overlap. Okay. However, there is an overlap here between these two sequences, and they both are our sequence, our target sequence that we are looking for. And the overlap is in this one. This one is shared among these two sequences. And since we, in this example, we allow overlap, so we highlighted it, okay? But if you don't allow overlap, then this is not going to be detected. This shouldn't be detected, and you should be able to derive both the state diagram for allowing overlap and for not allowing overlap. Okay, try it yourself for this sequence. Okay, for this exact sequence, and show me if you want, and I will tell you whether this is correct or not. Okay. All right. So this is about sequence detection. So it's you have a variable length stream of bits or a string of bits, and you are looking for the sequence at any place, showing any place. And if you are allowing overlap, it could be overlapping. Two sequences could be overlapping or sharing some bits together. Okay. Now for the code, a code is basically a fixed length string of bits. Okay. And every bit in the code has a position and a value. Of course, a value could be 0 or 1, and it has a position. Basically, it's a weight. Okay, not only just a value, but it's also a weight. So your the target code that you're looking for must match both the weight as well as the value. Okay, so let's take an example: a 3-bit code that detects the code 011. Okay, that detects the code 011. So in the code, we don't basically treat the code like this as a one string, one chunk, one big chunk string like this. No, we divide our code into words. Okay, each word has 3 bits, which is basically one code sample. Okay, so we have 101. This is one code. 010, and then on so on and so forth. Okay, so our sequence here appears here. Okay, only here. And notice, even though we have 011 here, but it shouldn't be counted because this belongs to 2 codes. Okay, it belongs to 2 codes, so it shouldn't match your code. Okay, so the only place that in which we observe this code, okay, is this one here. Okay, 011, and it matches both the value and the position. Okay, however, this one has, for example, in this one, this is position 0, whereas this one is position 2. This one is position 2, and this one is position 1. This one is position 0, and this one is this one is position 1, and this one is position 0. So they don't match with respect to position. Okay, they have to match both with respect to position and value. Okay, otherwise it doesn't count. Okay, it doesn't count. So this one does not, even though it matches the code bits, but it has to be ignored if we are building a code detector. Okay. All right. Now, having said so, we are ready now. Okay. So just make sure that you get enough practice for these 2 applications. Now we move on to a different application, which is arithmetic circuit or serial arithmetic circuits. Okay. We would like to be able to compute arithmetic results serially. Okay, so the third application for clocked sequential circuits is arithmetic or serial arithmetic computation. Serial arithmetic computations. Computation. Okay, so basically what I mean by that is that you have a circuit, a clocked sequential circuit here, clocked sequential circuit, and it is receiving a single bit input X that changes at every clock cycle. Okay, and it produces the result as it changes. Okay, so for example, this is why. Let's say that we derive. Let's just example derive a Mealy type state diagram. For a circuit, let's say for a clocked sequential circuit that has one serial input or 1-bit serial input, that has 1-bit serial input X and 1-bit serial output Y. Okay, I'm using lower and uppercase interchangeably here. Okay, they mean the same variable. Okay, big Y and little y, they mean the same variable. All right, so let's take an example before we proceed. Okay, so X basically, if you want, for example, okay, but I haven't yet determined the operation that we would like to do. Okay, basically Y should be the circuit should compute Y X plus 1. Okay, X plus 1. So if you, for example, if you would like to compute X plus 1 for X equals 5, for example, then you have to serialize 5 1 bit at a time. So let's see an example, or let's see how this circuit works, like in a tabular manner. Okay, so we have the clock, okay, and we have X, and we have Y, okay? So this is clock number 1, 2, 3, 4, okay? Now, we have X, for example, 5. We will input X from the least significant bit all the way to the most significant bit. So 5 is what? Let's say, no, let's pick a number that differs, that is not symmetric. Okay, so let's pick, for example, 6. Let's, for example, here, this example takes X equal 6, which is in binary 110. Okay, so we'll start by inputting the 0 first. 0, and then 1, and then 1. Okay, my Y should be 7. So my Y should be computed serially as well. Okay, so for this, at this clock cycle, my Y should be 1. Okay, at this clock cycle, my Y should be 1. Okay, and at this clock cycle, my Y should be 1. Okay, so because X, which is 6, X is 6, Y should be 7. Easy. Okay, it's easy. But how do we do that? This is a question. Now, how do we serially compute that? Now, after this, after you finish entering X, you can stop the clock. You can stop the clock so that you no longer provide, you don't need to provide any more information, any more bits of X. Okay, so the way we are doing it is that we are storing the carry. The carry will deal with the carry as our state. Okay, the carry at each state will be our, or the carry at each stage will be our state. Okay, so initially my carry will be 1. Okay, why? Because basically I need to compute X plus 1. So at the initial state, I need my carry to be 1. Okay, and then depending on X, I will output either 0 plus 1 or 0. So depending, so here, okay. So initially, I can say initially, carry n equals 1. Okay. So at the first clock cycle after resetting the circuit, I can say at the first clock cycle after reset, my y, which is equal to x plus, I said the carry in, right? The carry, which is initially 1, the carry, okay, which equals x plus, okay, 1, okay, initially. So this depends only on the value of x because the carry is constant at the beginning. Okay, so it could be if x is 0, then the y will be what? Y will be 1. And the new carry will be 0 in this case, okay, because it's 1 with a carry of 0, right? But we don't write the 0 here, we don't need it. If x is 1, then we have y will be 2, okay? 2, which means 0 with a carry of 1. 0 with a carry of 1, so your carry will be 1. So we have, we start with a carry of 1, and we wind up with another carry of 1, okay? So our initial state will be, okay, which is S initial. I'm going to annotate the carry here, okay? My carry, it's not the output. This is not the output. Okay, let me do it another way. Maybe. So I will say S sub J, okay, is the carry, the value of the carry of carry N is J, okay? So if I say S sub 1, it means that the carry in at this state is 1. S sub 2, it means the carry is 2, and so on and so forth. So at the beginning, the first state I have is S1 because initially my carry is 1. Okay? And then I said that if X is 0, remember, I said that if X is 0, then I should what? I should output a 1. So my Y is 1, and my carry will be 0. So I should have another state here, S0, okay, which means the carry is 0 here. And if my X is 0, I should output a 1 and go to the carry 0. And this is, by the way, this is my reset state, that we don't forget, okay? Next, if I am in S1, what does it mean? Again, I'm repeating that. I'm repeating myself here. It's important to understand. S sub 1, it means that the value of the carry here is 1, okay? So we start with 1, and then the carry will evolve as we compute, okay? As we progress in the summation, okay? So if the input X is 1, then you see here, I'm going to have a carry of 1 for the next state, and the output will be 0. So this is carry of 1 means I'm going to back to S1, okay, because S1 means the carry is 1, okay, if this is 1 and the output is 0, okay. Now we need to compute what happens, what are the transitions in, if we start from S0 now. From S0, we can have, so S0, what does it mean? It means that Y equals X plus the carry N, which is 0. So it equals X exactly. So there is no carry whatsoever, okay? So it means that if X is 0, my Y will be 0. If X is 1, my Y will be 1. So this is what it means, 0, 0, and 1, 1. Okay, so this is the final state machine for the incrementer circuit, okay? The question to you that I want you to pause the video and try to answer it yourself is, how many flip-flops do we need to implement this circuit? And the answer, if you paused and I hope that you reached the conclusion, since we have two states, okay, it means that our states will be, if you do the state assignment, it will be 0 and 1. That's it. You have to, it's 1 bit. So you need only one flip-flop to implement this, okay? And it is very simple. So I'm going to show you the implementation here, only here. And for the next problems, I'm going to show only the state diagram, okay? So for implementation here, let me say, well, S0 is assigned 0 and S1 is assigned, or you know what? Let me just reverse them because I want to reset my flip-flop, okay? My S1, I'm going to assign it state 0, and my S0 is going to be 1, okay? Well, it makes sense that, you know what? It makes sense that I encode the value of the flip-flop to be the carry, okay? So I'm going to assign S1 to be 1 and S0 to be 0, okay? So when I have to make sure that I use the proper reset mechanism now. Okay, so I have a present state here. This is my 2D state table now. Present state, which is, let's call it A, for example, or Q, you can just call it Q, which is either 0 or 1, all right? And I have the next state for X equals 0 and for X equals 1, and my output Y for both X equals 0 and X equals 1, okay? So my next state is A plus here, A plus here. And we used to call this output here, okay? Output, and this is Y, and Y here, and Y here. Okay, so when I am in state S0, this is the first row here, and I receive a 0, whether you receive a 0 or a 1, you stay in S0, so this is going to be a 0, 0. And if you receive a 0 for X, your output will be 0, and if you receive a 1 in X, your Y will be 1, okay? It follows X, okay? Follows X. If you are in state 1, on the other hand, and you receive a 0 for X, then you'll move to state 0, and your output will be 1. If you are in state 1 and you receive a 1, you will stay in state 1, and your output will be 0. Okay. So this is really simple, really very simple to implement, okay? You can see that A plus, okay, is it's a two variables K map basically, okay? It's this min term here. Okay, so my A plus will be what is it? It's going to be A ended with X, okay? And my Y is going to be XOR, basically, okay? The XOR when, so if A is 0, whenever A and X are different, okay, whenever A and X are different, it will be 1. So it's A XOR with X, okay? It's obvious because this is obvious because basically this is addition. Remember, for addition you should expect XOR gates, okay? So now you have your D flip-flop now, D, and this is your clock, C, and this is your Q, and this is A, okay? So the output here is A, and you don't need actually a complement, but I'm going to just put it here, okay? And for A plus, you need an AND gate. We have A, and we have X. And for Y, you just need an XOR gate that takes what? A and X. So this is basically the circuit, okay? It's a serial incrementer, okay? Let's try to validate our claim that this does serial incrementation, in fact. Okay, now let me try to trace. We are going to trace this circuit for the value that we claimed that it should work. Okay, so I'm going to do this now, but using the state diagram rather than the value that we know. Okay, so according to the state diagram, we start with S1. So I forgot the reset here. So this is going to be actually, I need to put this as asynchronous sit and hook it up to reset. Why is that? Because my initial state is when Q is 1. So I need to make it a sit, not a reset. Okay, sit. Okay, so when reset is 1, is asserted to be 1, this is the external input I'm talking about. When reset is asserted to be 1, we need to make sure that the flip-flop is 1. Okay, the value of the flip-flop is 1. Okay. All right. Okay, so so I have here, let's say that I have X, okay, and I have Y, okay, and we used what was the example? It was 0, 1, 1. Okay, I'm going to repeat that. 0, 1, and 1, and let's see whether we get 7 for Y or not. Okay, so initially we are in state S1, and we receive a 0. Okay, so my output will be 1, and I go to state S0. Okay, let's just put the state as well so that we know what we're doing. So the state, the present state, which is A, basically. We denoted it by A here below. Okay, so A is S1 at the beginning. And then after this 0, we go to S0. Okay, and the output here is 1. Go to S0. And then we have a 1 here. A 1 here, okay, with S0. So the output will be 1. Okay, you see that? You see that? So if you get a 1 here, you get an output of 1. And if you get a 0, you get an output of 0. So again, we go to S0. So once we move into S0, we are trapped there. No way of getting out of that, okay? Unless you reset your machine for another input. And then you get a 1, another 1. So this is 1. So this is exactly what we're looking for. If you feed it with 6, you get 7. Okay, let's see another example. Let's feed it with, for example, let's say 12. 12. Or no, let's say, for example, 11. Okay, 11. So 11 is what? 1, 0, 1, 1. Okay, so we have 1. So starting with the least significant bit, and then 1, and then 0, and then 1. Okay, this is the most significant bit, and then this is the least significant bit. Okay, so initially I am in S1. Okay, and I receive a 1. I stay in S1, and my output will be 0. Okay, and then I get another 1. Okay, so I stay in S1, and my output will be 0. Right? This is why is that? Because if I receive a 1, this is what's going to happen. 1 with the output 0. Okay, then I stay in S1. Okay, and then I receive a 0 eventually. Okay, at the third clock cycle, I receive a 0, and then my output will be 1, and the next state will be S0, and then I receive a 1 in S0, and my output will be 1. Okay, and then I kill the clock. I don't want to continue. Okay, so let's see. So this is 11, and this is 12. So it is correct. Okay, it is correct. We validated it using 2 numbers, and you can validate it further using different numbers as well. Okay, so let's take a little bit more complicated example for arithmetic circuits. Okay, let's implement this circuit instead. Okay, so another example. melee type for, I'm not going to write the question from the but you know what I mean, okay? We would like to derive a melee type state diagram for the serial computation of computation of y equals 2 times x plus 1. Okay, 2 times x plus 1. All right. So this will be easy. Okay, so again, the constant part is your carry. All right, constant part is your carry. So my initial carry will be 1. Okay, so I have initially my S1. All right, initially the carry will be 1. So this is my initial state. Okay, reset. Now I can have my y initially is equal to either, actually let me just do it this way, if x equals 0 or x equals 1 initially. This is the initial state. So my initially, it means my carry n is 1. Okay, if my carry n is 1 for x equals 0, then I have 2 times 0 plus 1, which is 1. Okay, so it's a 1 with a carry of 0. Okay, 1 with a carry of 0. So if I receive a 0 here, then my output will be 1, and I go to state S0 because my carry is 0 now. However, if I receive a 1, then what happens? This is going to be 2 times 1 plus 1, okay, which is 3. So it's 1 with a carry of 1 in binary. Okay, 1 with a carry of 1. So if I receive a 1, I stay in S1 and output 1. Okay, so it's this is the output here, and this is the carry. Okay, now you are in S0, and you receive either x being 0 or 1. So this is for S1. For S0 now, your y will be x equals 0 and x equals 1. Okay, the first branch will be 2 times 0 plus 0. Okay, S0 means the carry is 0. Okay, the carry in is 0. So this is equal to 0 with a carry of 0. So when I have my input is 0, my output will be 0, and my carry will be 0. Carry will be 0 means I'm moving to S0. Okay, and when my x is 1, on the other hand, I have 2 times 1 plus 0. So that's 1 0 in binary. So this is 2, and in binary it is 1 0. So it's 0 with a carry of 1. And now I go back to the carry 1. Okay, but my output will be 0. Okay, my output will be 0, but the carry is 1. Okay, so we covered all the states, and let's see whether this outputs the correct result by tracing it. Okay, so my x, now let's suppose that I have this is the present state, which is, let's call it A, for example. Okay, and or let's call it present state without, because we haven't implemented this circuit, and I don't intend to implement it, because you already know how to implement the circuits now. Okay, the sequential circuits or synchronous sequential circuits. We have given enough examples for implementation. So this is the present state, which is S1 initially, and my x is going to be, let's take, for example, let's take x equals let's say, for example, 7. Okay? 7 means no, let's take something that is not symmetric. For example, again 11. Okay, which is 1 0 1 1. Okay, so it's from, of course, you start from the least significant bit. Okay, so 1, 1, 0, 1. What do we expect the output to be? We expect the output to be, this is binary and this is decimal, okay? We expect the binary to be, the output to be 2 times 11 plus, 2 times 11 plus what? 1, okay, which is 23. What is 23 in binary? 16 plus 7. So 16 plus 7. This is this should be the output, okay? So we should expect 5 bits in the output. So we should expect to see a carry. So in addition to the last bit, so we should, for example, if we would like to see the output, all the output bits in the output Y, we should put a 0 at the end because we need to see 5 bits of output. Okay. So this is the number. So it's 0 1 0 1 1 0 1 0 1 1, which is 11. Basically, a 0 to the left of the most significant bit doesn't affect the number. Okay. And this is Y now. My Y will be what? Let's not confuse ourselves. So initially I have 1, so my Y will be 1, and I'm going to stay in S1. Okay, just by the state diagram. 1, output will be 1, and I'm going to stay in S1. Okay, again, it's the same thing. 1, and I'm going to stay in S1. All right, but here now I get a 0. 0 means I'm going to have an output of 1, and I'm going to S0. So this is the next state, and my output will be 1. Okay. In S0, I have a 1. In S0, I have a 1. So I have an output of 0, and I go back to S1. Okay, S1, and my output will be 0. And in S1, I get a 0. So my output will be 0 in S1. 0 in S1. It means that my output will be 1, and my next state will be 0. And so this is 1, and then S0. Okay, so this is 1, and then we stop here. Basically, we stop here. All right. So you can see that this is the expected output. Okay, but it's basically from it is output serially from the least significant bit to the most significant bit at the 5th clock cycle. Okay. Let's take another example involving subtractions now. Okay. So let's implement. By the way, arithmetic circuits are best derived using Mealy machines. Okay. If you try to derive it using a Moore machine, it will be really a pain in the neck. Okay, it's not easy to implement it using Moore machines. Okay, so we have an example here. So we would like to implement Mealy type machine for Y, serial computation of Y equals X minus 1. Okay, so it's a serial decrementer. Okay, so now we have to use a trick. Okay, we have to use a trick because we don't want to use the borrow logic, but rather we would like to use 2's complement. Okay, now what is the 2's complement of minus 1? It depends on X, right? It depends on X. What is the length of X? Okay, so we don't know that ahead of time because we are serially taking X bit by bit. Okay, however, minus 1 has a special code in 2's complement. It's minus 1 is always all ones. So if you have an n bit representation of minus 1, okay, in 2's complement is always in bit of 1. Okay, this is the replication operator. Okay, replication operator. It means that I'm replicating this 1 n times. Okay, so basically this equals to 1 1 1 1 1 1. Okay, how many times? N times. Okay, so as long as I'm performing the addition or the decrementation, as long as I'm receiving bits of x, I'm going to add 1 to them, okay, to simulate the subtraction. Okay, so basically it means that at every clock cycle, I'm going to have y, okay, is equal to x plus 1, okay, all right, this is going to be always happening, okay, plus the carry n from the previous stage, okay, and initially my carry n is 0. So my S0 now, my state is S0 at the beginning, all right, and when my so again the state, the index of the state indicates the carry n at every state, okay, so initially my carry n is 0, okay, and at every state I increment or I add 1 to x. This is by the 2's complement, because you know that this minus 1, it means all ones all the way until x is over. So it means that I'm adding 1 to the first bit of x, the second bit of x, third bit of x, and so on and so forth, always adding 1, okay. So this is the constant part of the equation. The variable part of the equation is this one, the carry n, okay. There's the carry n, we encode it using the state, okay. The state initially is 0, okay. So we have for S0, okay, we have y, which is for x equals 0 and for x equals 1, okay. For x equals 0, it's going to be 0 plus 1 plus 0, which is 1, okay, because my carry n here is 0, okay, for state S0. My carry n is 0 for state S0. My carry n is going to be 1 for state S1, and so on and so forth, okay. So this is a 1, with a carry of 0, okay. So I'm going to stay, I forgot to mark the reset state here. Okay, so if I receive a 0 for x, I'm going to stay here in this state because my carry out is going to be a 0, but my carry in, my output is going to be 1. Okay, next, if I receive a 1 for x, here it's going to be a 1 plus 1 plus 0, okay, which means it is in binary, it's 1 0, okay, in binary. So it's the output is going to be a 0 and the carry is going to be a 1, okay, carry is going to be a 1. So I need to go to another state in which the carry is 1, okay, and this is when I receive x being 1, the output will be 0, okay, the output is 0, okay. Next, okay, so this one here is check, done, because we covered the 0 and we covered the 1. Now this one here, if I'm in S1, my y will be either depend on the value of x equals 0, x equals 1, okay. So for x equals 0, it's going to be 0 plus 1. This is a constant 1, it's always added, okay, it's always added. Now this is the variable part, which is plus 1. This is the carry m, okay, it depends on the state, okay, and this is going to be a 1 0 in binary, okay, again. So it's we output a 0, okay, for an input of 0, we output a 0 and we go to state 1 because the carry out is 1 in this case, okay, the carry out is 1. This bit is the carry out here, it's 1, okay. If we get a 1 on the other hand, 1 plus 1 plus 1 is going to be a 1 1 in binary, okay. So the output is going to be a 1 So you get a 1, the output is going to be a 1, and you go back to state S1. So this is the whole circuit, the whole state diagram for x minus 1. Okay, what is the difference between this and x plus 1? If you let me just bring that one to here so that we differentiate between the two. Okay, so you can see that incrementing and decrementing is very similar in binary. Okay, in binary it results in a very similar state diagram. Okay. Okay, now the difference here is going to be this bit here, and of course the carry will be different. Of course, okay, carry will be different, and the output is inverted. Okay, and you can imagine that this is the case because in decrementation we use 2's complement to do that, and 2's complement involves 1 complement plus 1. Okay, 1 complement plus 1. All right. So this is for x. This is for x minus 1, and this is for x plus 1. Okay, let me just erase this one. Yeah, so that we validate our design. Now we will trace this state diagram for x equals, for example, again, let's say 1 0 1 1. Okay, x equals 1 0 1 1. Okay, so notice that I'm giving x more than 1 bit. Okay, but this should be understood that it means that x is going to be fed to the circuit 1 bit at a time. Okay, starting from the least significant bit. So this is the present state, and then x, and then y. Right. So the present state initially is 0, and then x is 1 1 0 1. Okay, and so I am in S0 and I receive a 1. What happens? You go to S1 and your output will be 0. Okay, and I am in S1 now and I receive a 1, so my output will be 1. Okay, I am in S and I stay in S1. Okay, when you enter S1 you don't get out. Okay, so I'm going to fill in this one. Okay, again. Okay, so you are in S1 and you receive a 0, so 0 1. Okay, so what's the output here? You can see that this is 11, this is 11, and this is output here is 10. Okay, in decimal. Okay, so 11 minus 1 is 10. Okay, so this is tracing the sequential or state diagram. Okay, it's a skill that you need to learn. Okay, you need to be able to trace the state diagram. Okay, let's take another example. Let's take another example for a very simple, or another. Let's say it's not. Let's call it not. Let's not call it simple. Another example for an arithmetic serial computation of this arithmetic circuit. So we this by the way, this appeared in the exam last term. So we would like to derive the state diagram of the circuit, or Mealy type state diagram of the circuit that computes y equals 1 minus x serially. Okay, 1 minus x serially. Again, you should revert back to what we call the 1's or 2's complement. Okay, so in 2's complement, this equals nothing but 1 plus what? X complement plus 1, right? So this is basically x complement plus 2. All right, now this is your carry, initial carry, and you should always add that to x complement. So let's do this quickly and then stop here. Okay, so I have S2 at the beginning, as my carry initially is 2, and this is my reset state. And if I receive, so in S2 here, my y will be when x is 0 and when x is 1, okay, my y will be 0 complement plus 2, right, which is 3, okay, which is 1, 1, okay, so we have a 1 in binary, 1 with a carry of 1. So we go to another state S1, okay, and if I receive a 0, then I output a 1 as well and go to S1, okay. If I receive a 1 on the other hand, it's going to be a 1 complement plus 2, right, which is 2, nothing but 2, so it's 1, 0 in binary. So it's a 0 with a carry of 1. So again, same next state here, 1, you get a 0 with a carry of 1, okay? 0 with a carry of 1, okay? All right. Now you are in S1, and y will be depend on value of x, 0 or 1. So S1 means the carry in is 1 now. So we have 0, 0, and x is 0, so x complement will be 1, okay? Plus 1, okay, which is 2, so 1, 0 in binary. And so if x is 0, I go back to S1 as well, if x is 0, but my output will be 0. And if x is 1, it's going to be 0 plus 1. So it's going to be a 1, okay? So 1 with a carry of 0. Okay, so we have a third state here, S0, all right? So if my x is 1, my output will be 1 and my carry will be 0, okay? Now this S1 is checked, okay? All the states have been, all the transitions have been covered. So now S0, 0, we have y, x0, x1, okay? For 0, x will be 1, x complement will be 1 plus 0, okay? I don't need to write that, but it's 1 with a carry of 0. And then for 1, it is actually 0 plus 0, so it's 0, 0 with a carry of 0. So 0 with a carry of 0, and 1 with a carry of 0. Actually, if x is 1, I get an output of 0, and if x is 0, I get an output of 1. Yeah. So when x is 0, I get an output of 1, and when x is 1, I get an output of 0. Okay. That's it. You don't need any further state. Okay. So let's just trace this to make sure that this is correct for the same value. X equals again 11. Okay. 1, 0, 1, 1. Okay. So what should be the output? Okay. Let's pick. Okay. So 1 minus 11 will be minus 10. So my output should be how many bits? Minus 10 means my range should be minus 16 to 15, or plus 15. So it's basically 5-bit, yeah. So I need to append the 0 here to just for the case for matching the number of bits. Okay, so this is my present state. Okay, and this is my x, and this is my output y. Okay, so my present state is S2 initially, and I enter the bits of x from the least significant to the most significant bit. 1, 0. Okay, what's the output that we expect? It's minus 10. So because basically 1 minus 11 is 10, is minus 10. What is minus 10 in 2's complement? Basically, it's so 10 in 2's complement is going to be 1, 0, 1, 0. Okay, and minus 10 is going to be 1, 0, 1. Okay, this is minus 10. Okay, just if you're not sure about this, review your 2's complement arithmetic, okay? Basically what I did is to take these two as is and then complement the rest of the bits, okay? Complement the rest of the bits. So we expect the output at y to be 0, 1, 1, 0, 1, okay? We get this, then this is correct, okay? So we are in S2, okay? We are in S2, and we receive a 1, okay? If we receive a 1, then the output will be 0, and we go to S1, okay? We are in S1 and we receive a 1. Just follow me. Receive a 1, we go to S0, and the output will be 1. Okay, the output will be 1, and we go to S0. We are in S0. This is a terminal state. We can't leave now. Basically, the output will be the complement of the input, okay? The complement of the input. So S0, you get a 0, you get a 1 here, okay? And a 1, you get a 0, and then another 1, another 0, you get a 1. Okay, isn't it the expected output here? It's 1, 0, 1, 1, 0. And this is 1, 0, 1, 1, 0, okay? And it's basically, this is the expected output. So this is correct. Let me stop here. If you have any question about it, about this material, please let me know. And I will be glad to answer all of your questions.